y no sé qué, ¿no? Ok, pues gracias a Ricardo porque él es el que me invitó a dar el minicurso y al parecer organiza otros minicursos, entonces hay que poner atención cuando mande un correo por ahí, ¿no? O lo que sea. Entonces me pidió que dé un minicurso en inglés, ¿verdad? So thanks to Ricardo because he's organizing all these mini courses which are very nice, and in particular he's organizing mine. And he asked me to give this QFT in curved spacetime PhD mini course, right? So I thought I'd first off I'll maybe give you a bit of bibliography that you're not going to read. Then I'm maybe going to give you some motivation, and then I'll tell you what we're going to do. And in particular, what we're going to do today. But also the rest of the days. Okay? So let's start with bibliography in case you want to read something. I'll write it in order of readability. One means everyone can read it. And the first reference is Birrell and Davies. This is a classic monograph from the 80s, and it's really the first attempt to write a bunch of the results of what people were doing. This is already after Hawking did his amazing paper with black hole radiation and all that. And this is really very readable in case you want to have a look at it. And it has a lot of physics. Very little mathematics, but it has a lot of physics. And it's remarkable in that sense. Another piece of bibliography that might be readable is some lectures by Chris Fuster from the Max Planck Institute. So let's say this is lecture notes from Max Planck. Okay, from the Maths Institute, I think, in Leipzig. This is introducing already some of the modern ideas of algebraic quantum field theory, and this is the main source where I started learning the subject. Well, first I learned from Birrell and Davies, but then from the algebraic perspective, that source is very good. Then there's the classic monograph by Fuling from 1989, which is excellent, especially for flat spacetime, I think. Then there's Wald's little red book from 1994, which I guess you know if you've more or less, I mean, it's a very popular book. And then there's some modern algebraic QFT book edited by a lot of people who are sort of more mathematically inclined. And this book I really think that you shouldn't read unless you're interested in some very specific mathematical detail, because I will not be very mathematical. But this book contains stuff that I cannot read. Okay? And so that's it. This you should read for sure. This is very nice to read. This you should also maybe have a look and for more details. And this I really think that only if you're really going deep into researching this subject and so on. Okay. So now let me say why I would like to talk to you about this. other than being invited to. And well, of course, there's several points, right? I mean, so for once, there's no quantum gravity at hand, okay? And in the absence of quantum gravity, quantum field theory in curved spacetime is the best thing we can do at the moment. But also, we know that, we know that the Earth is not perfectly flat. So we should better be able to describe quantum field theory at least with light curvature. And it better have a description that is quite similar to what we usually do when we do mode expansions and then change some stuff to operators and so on. And so we know at least that spacetimes, lightly curved spacetimes on Earth, for example. And we know that quantum processes happen on Earth that has light curvature. And they happen in the solar system with neutrinos that come from the sun and change. There's these neutrino oscillations and so on. Other reasons to study this is because there's some quite amazing predictions. So, for example, there's the black hole radiation prediction. There's the Unruh effect. There's cosmological particle creation. This is cosmology. And all these effects are predicted in the framework of curved spacetime quantum field theory. And they're really worth studying. So even if you're a theoretical physicist in general, you should know a little bit about them. And of course, related to this point is semi-classical gravity. Namely, replacing matter by quantum stuff in the Einstein equations and try to do the best we can with that. But finally, there's mathematical interest in general. So it turns out that if you want to do quantum field theory in curved spacetimes properly, you're forced to do a lot of stuff. And you end up in an intersection of many interesting mathematical subjects. And so quantum field theory in curved spacetime can be regarded as a field of mathematical physics of interest in its own right. So it's very rich in that sense. But okay. So I don't know how fast I'm going. But let me tell you what I plan to do very quickly. So today I plan to do a couple of things. I want to talk very briefly about geometry. And then I want to do quantization in flat spacetimes so that everyone remembers how to quantize stuff. Because people here, did everyone take quantum field theory and GR? Or mostly GR, or mostly QFT? GR. Okay, so this is going to be useful to level the... And what about you? Did you take GR and quantum field theory?
Yes, I did. Both of them.
Okay, good. Well, then on the next session, I want to look at the Unruh effect. And this will really start hinting at the problems that you have with the standard approach to quantization. Because this is an effect that happens already in flat spacetime, but it's quite revealing. I'll tell you what it is next time. But it's essentially the fact that if you move in an accelerated frame in Minkowski, the vacuum looks thermal to you. Okay, that's the effect. And then I'm going to revisit B to sort of try to look at this from a different perspective. So far this week we're going to be in flat spacetime, as you can see. And then next week, what I plan to do is to look at the algebraic approach. So I want to change the framework, right? And show you how that facilitates talking about quantum field theory in curved spacetimes, and how this is one of the right ways to look at it. There's other ways. There's, for example, topological QFT, which is also very powerful in curved spacetime, but I'm not going to talk about that. I'm going to talk about the algebraic approach a little bit. And then I'm going to talk about states and the renormalization of the stress energy tensor. Okay, so TAB renormalization. And at this point, it's crucial that you have the right state so you can renormalize it. So not every state is going to give you renormalized stress energy tensor. And finally, on the last day, I'm going to talk about some fun stuff, which is black holes and Hawking and info loss, so the information loss puzzle. Okay? And maybe, as requested, I will talk a little bit about QFT in non-globally hyperbolic spacetime. Spacetimes. And I'll tell you what that is. Actually, I'll tell you today what a non-globally hyperbolic spacetime is. So most of the time, I mean, actually, practically, I think all of the session, unless I decide to go a bit further in point E, I'll just focus on a free Klein-Gordon field. And that's going to give us enough to have fun. And most of the time, I'm going to talk about globally hyperbolic spacetimes, except in this very last day. Actually, in both points G and H, I'm not going to be using globally hyperbolic spacetimes. Okay, so that's my plan. So if you find one session that is a bit boring, you can skip it. No problem. So let me start with the geometric preliminaries. First of all, I'm going to say that I adhere to a convention where everything is 1. So speed of light, reduced Planck constant, and Newton's constant is 1. Unless stated explicitly, this is, what we're going to use. And in terms of geometry, we will typically consider spacetimes as 4 tuples meaning that there's a topological space. It's equipped with a metric that is Lorentzian. So, how do I call that? Signature of G equals. And I'm going to use this convention, dot, dot, dot. I'm going to deal only with orientable spacetimes, which means that you have a top form. I think everyone here knows what that is, which is everywhere non-vanishing and gives you an orientation. And I mean, it keeps pointing in one direction. It gives you an orientation. It's a volume form, right? And then we have a vector field T that is everywhere time-like. So that means that GT is negative. And I'm going to use often abstract index notation. Is everyone familiar with that? Yeah, so that means that I can write this as this. Okay, and this is not a coordinate, it's just an abstract index that if it's up, it tells me this is a vector, and if it's down, it tells me it's a covector or something more complicated, or in this case the metric has two covector indices. What else?
So are you going to use wall convention?
Yeah.
Or using Greek in the
Greek for coordinates. Yeah. And okay, so more preliminaries. What we'll typically consider solutions to Einstein's field equations, because that's the case of interest. You want to do quantum field theory in some space-time that is sensible. So, namely, solutions to that. Okay. And often the approach is that when you do quantum field theory in curved spacetime, usually the approach is that the field is so weak, it's just propagating on the spacetime, so that it doesn't have a back reaction, and if you will, it doesn't contribute to this equation. It's a quantum perturbation on top of the Einstein field equations, if you will. And you do not do back reaction. Tupac, hello. And you do not do back reaction unless you want to do semi-classical gravity. That's a different story. And I will probably not touch the subject very much, except for maybe here just comment on it a little bit. Okay. Right, and a bit more conventions. Well, you all know that this is Einstein's tensor, where R, A, B, C, D, V, C. This is the Riemann curvature. This is the covariant derivative with respect to some connection, typically the Christoffel-Levi-Civita connection. This is the Ricci scalar and Ricci tensor, and this is the Ricci scalar, which is just a trace of the Ricci tensor. A bit more convention. There's a few useful notation bits for causal structure and so on and so forth, which I may give now, but or should I give it when I look at states and so on? I'll do it now. It doesn't really hurt. Okay. So, so we say that a point P1 in the space-time is in the chronological future of a point Q. We denote that by I plus. If you can get to P1 from Q with a time-like curve. And there's a similar notation for the chronological past of Q. And there's a similar notation for the causal future and causal past, okay? Which you denote by J. So namely that you can get from Q to R1 with a curve that is fully causal, or to the future, or you can get to R2, from Q towards the past. And we know what the future and the past is because we have time orientation.
I'm sure the students are not aware of what causal curve means.
Right. So suppose you have a curve that is the integral of some vector, namely, so you have a curve that has a tangent vector v at every point along the curve. So you know v, as we said, if v satisfies this, then it's time-like, and the vector, being everywhere tangent to the curve and always time-like means that this is a curve that is chronological, so namely contained to the future of a point. So you can integrate from one point to another along this vector, and the 2 points are going to be connected by a time-like curve. A curve that has everywhere a tangent vector that is time-like. Well, you get a causal curve if you have this. Okay, then this is causal. So when it goes to 0, you call that null. A null vector is when its contraction with itself against the metric is 0. You call that a null vector. And so you call a causal curve if everywhere tangent to it is a vector that has this property. So it has to be time-like, but sometimes it can be null. Or it can be null all the time, but it cannot be space-like. So what you cannot have is this. So this is space-like, okay? So this is no. So let me draw a little picture, because I gave them different letters so I could draw a little picture, right? So this is the point Q. P1 is up here. P2 is down here. So there's a curve that connects to here and to here. Well, let me put the point there and put the point here. And R1 and R2 are here. This is R1 and this is R2. Particular note that the curve connecting to R2 so R2 is also in I minus Q, but that's just one example. R1 is really not in I plus Q, but it's really connected along this null curve, okay? So that's a little example. Similarly, if you have a set, okay, if you have a set in M, you have similar definitions, and this is S, and you have similar definitions. You just draw a cone like that, and you call this I minus S, I plus S, and including everything, you call them J plus S and J minus S. So J plus and J minus include the interior of these cones as well, okay? And so you would say that all these points, for example, are inside I plus S and inside J plus S, but you would say that if you add these points, for example, they're inside J plus S but not inside I plus S. Okay, so that's just some conventional stuff. And well, I have a little comment I wrote a little comment to make a technical comment, but I think I don't need to. All our spacetimes are nice, and there are never problems. There are never missing points or things like that, okay? So my final comment on geometry. This is very good because I've only done half an hour now. So my final comment on geometry is the following. As I said, most of the time and most of the time in our little course, and most of the literature, people that worked in curved space-time quantum field theory work on globally hyperbolic spacetimes. So I'm going to tell you what that is. And it's a very simple definition for which I have to define something else. So, definition in 2 kicks. So, let sigma in M be an surface. So achronal means what you think it means. It means that it doesn't have 2 points, one to the future of the other. Okay? And a surface means what you think it means. It's it's a cross section of the manifold. Okay? An achronal surface, more generally, it can be an achronal set. Right? So, let me write that, i.e. each. So this is the technical definition of achronal surface. Each time like curve in M intersects sigma at once. So I cannot have a time like curve that intersects sigma twice, because then I could put 1 point to the future of the other using my time orientation. Okay. And let sigma be such that every inextensible causal curve in M intersects sigma. So what does inextendable mean? So remember, a curve is a map from R to M. So in particular, I use some parameter for the curve, and it gives me a point in the manifold. So for example, if this is a manifold, I can go from this interval to this curve by gamma. Okay? And inextendable means that that really that you cannot extend the domain of this curve. So t is already the whole of R. It goes from minus infinity to plus infinity. You cannot add more t to keep going with the curve. So that means that you cannot extend the curve. It cannot give you more points here. Of course, it's a continuous map. Everything that we do in this thing, unless stated otherwise, will be smooth, nice, blah, blah, blah. Well, sometimes you cannot be smooth and nice with quantum field theory because you have to deal with distributions, but then I'll tell you and we'll work it out. But the point of inextendability is this, right? That's the idea. Okay, so sigma in M is an achronal set or surface such that every inextendable causal curve in M intersects sigma. Okay, so every inextendable causal curve crosses sigma, and time-like curves intersected at most once. Okay, then sigma is called a Cauchy surface. Cauchy surface. Okay. And if sigma in M is Cauchy, then M is, actually that's a double arrow, globally hyperbolic. Let me write it. Globally hyperbolic. Okay? In practice, Many spacetimes that we like are globally hyperbolic. For example, Minkowski. Another example, the Rindley wedge. Another example, Schwarzschild. Plenty. Some of them that we also like are not globally hyperbolic. For example, if you take Reisner-Nostrom and you extend it as much as you can, it's not globally hyperbolic. ADS is not globally hyperbolic. Okay? So let me draw some pictures so that you get an intuition of what it means. And in doing so, I'll also give you more notation. Okay? So an example, Minkowski. Minkowski, which I'm going to omit orientation and time orientation and so on, and I'm just going to write it like this. Okay? Where eta you can write in your favorite coordinates, which look almost, well, let's do Rn. Your favorite sort of almost Cartesian coordinates, right? Well, let's do R4 because I'm going to do a little diagram now. Okay, so you can also write it. I'm gonna try to. Do you know how to draw a conformal diagram and all that, guys? Yeah, you do. Yeah. Well, we'll do it anyway for the ones that don't remember. So I'm going to introduce some null coordinates that are going to be of this sort. Well, first I'm going to introduce spherical coordinates. Okay. Okay. Now I'm going to introduce some new coordinates. UV, which are t minus r, t plus r, and I'm going to write this like that. Okay, so this is like that. Okay? Then I'm going to introduce new coordinates, which I'm going to call bar. And so notice that t and r go from minus infinity to plus infinity. U and v go from minus infinity to plus infinity. And hence, u and v lie in this interval. Okay? Because arctan looks like so, right? And this is and so what you do to bring infinity to u is you extend these coordinates like that. Just include the endpoints. And then you can see that as u goes to, say, plus infinity or plus minus infinity, u bar is equal to plus minus pi half, and similarly for v. So you bring infinity to a finite value of the coordinate. Okay? Principle, you could extend it to whatever you like, but then it wouldn't make much sense. And then you can, see where infinity lies, right? So to do that, it's useful to draw a little picture now, which is now the conformal diagram. So what you do is you write r equals 0 here, and then these null coordinates go in diagonal, but I'm suppressing the angle, so this thing really goes around. Each point is a two-sphere, okay? So at each point you have a theta and a phi coordinate attached to it. And here you say that v is equal to pi half. Here you say that u is equal to minus pi half. If you rotate it, you'll get also a future u bar and a future v bar, but whatever. Here, you say that v minus u is equal to pi. And here you say that v plus u is equal to minus pi, v plus u is equal to pi. And then you give names to these special points, right? So this is called, so let me redraw the diagram. So this is called scri minus. Well, because it's a script I, so people call it scri. This is scri plus, and this is future null infinity, past null infinity. This is space-like infinity. This is future time-like infinity, and this is past time-like infinity.
As far as I understand, scry is a letter from Scotland or something like that.
Oh, really? Okay, I didn't know that. I always just write script I. Anyway, so it has a lot of information because geodesics, null geodesics will land here. And in this conformal diagram, they will look really at 45 degrees, if you will. Time like geodesics, for example, if you stick at a fixed radius and go along the orbit of dt, end up here. And well, typically curves don't go here because nobody can move faster than the speed of light. Well, you could draw a curve, but it wouldn't be a curve with the significant, with no physical meaning, right? But you have to take into account that these are geodesics because, for example, a uniformly accelerated observer, which is everywhere time-like, can do that, will look like that. So that's a funny feature, this diagram. But it's of course only very asymptotically reaching those light rays. It never, but it keeps accelerating, so it keeps going faster, but it can never reach that null character. Anyway, this is globally hyperbolic. Why? Because every inextendable causal curve crosses this achronal set, sigma. And for example, I can set t equals 0, which is really a straight line like that. And every curve that I want to draw, well, let's say directed like that. Anyway, will always cross sigma. And it's really that simple. Okay. Now let's see how I'm doing with time, and I'll give you a non-example. And depending on how I'm doing with time, I'll be less or more thorough. And I think I will. Okay, so EG2, which is a non-example actually. And it's also a non-example modulo signs, which you have to check if they're correct, and so on. And factors of 2 and so on. Okay, sorry about that. And this is ADS. So ADS n. So it's n-dimensional ADS, which has the following topological manifold, and it has a metric which you can think of as embedded in a higher dimensional pseudo Riemannian manifold, but not Lorentzian. Okay? Okay. So it looks like a hyperboloid. And it's, so that's the metric, and you can see that I have n plus 1 coordinates, but then I can do the following identification. to lambda. And lambda is a cosmological constant. So this is the maximally symmetric solution for a negative cosmological constant. Actually, there's plenty of string theorists here. They will know if I'm getting the signs right and factors and so on, right? So anyway, you can put intrinsic coordinates and play a similar game to what I've done here with the angles and a radial coordinate and so on. And I'm going to call the intrinsic coordinates T, R, and everything else, okay? N minus. Okay. So these are the coordinates in space-time. And you can write the metric in terms of these coordinates intrinsically. And you can draw a diagram where you also forget about the angles and it looks like a box. And this is r equals 0. And this is space like infinity, time like infinity. And these little points are where null curves go. And you can imagine writing whatever surface you want, like that, for example. But there's a problem, namely that the t-coordinate is periodic. So these points get identified. So you can hardly write an achronal set, and you cannot have a Cauchy surface. Okay. There are other spacetimes. There are subspacetimes of these. For example, there's a so-called Poincaré patch like that. But there you can, you still, there's reason, I won't get into it, but sure.
Where would you draw a scribe plus and scribe minus there?
I think here.
In the corner?
Yeah. Plus minus. Where do I put it? Upstairs. Yeah. I'm doing this by memory, so. Okay. Okay, so that's everything I want to say about geometry. Just some conventions and just for the guys that don't usually do GR and so on, because we'll use some of these symbols, we'll mostly deal with globally hyperbolic spacetimes, and I want you to feel at ease with that. Remind you a little bit. So now I'm going to spend the rest of the time doing something very basic, which is I'm going to quantize a free Klein-Gordon field in Minkowski space. For the people that are masters in QFT, this will be a bit boring, but maybe it'll have a few elements that you haven't thought about. And for the people that are mostly from the GR community, this will be, of course, helpful. Okay. So I want to start with reminding you what the Klein-Gordon field is. So in a way that we all feel very comfortable, namely by writing an action. And I really want to do it in Minkowski space. Well, the action you can write in a general spacetime. Then I'll go to Minkowski, okay? You have a volume element. So typically you could write this in coordinates as square root of minus g. Well, let me be more so you don't get confused. Square root of minus the determinant of g dx and x, where x are your coordinates. And this just densitizes the volume element, right? So you can think of it like that, or you can think of it as a top form. It's equivalent, right? But this is usual physics literature, so that's nice. And then you write a spacetime metric here. And you contract with the covariant derivatives of a field that we're going to call the Klein-Gordon field. So this is a kinetic term. And then you can add a potential term, which is the mass term. And you can further add, when you're in curved spacetime, if you feel like it, a curvature coupling. Okay? So you can, so this now just looks like a potential to the scalar field. It's sourced by the Ricci scalar of the curvature. And it's a nice term to add because when you do the variation of phi to get the equations of motion, you still get a linear equation in phi. So that's nice. And the other reason why it's nice is because if you couple it to Einstein's equations, it doesn't really do much harm. So you could imagine, for example, coupling also this, right? With some eta, whatever, phi x squared. But this term would be horrible for the Einstein equations. This would really spoil many of the nice properties that the Einstein equations have. And in particular, I think it would spoil the well-posedness of GR coupled to the scalar field. So people, usually stick to this curvature coupling, okay? Well, so let me just say this is a real scalar, and this is the Klein-Gordon field. And it's classical. Okay, it's a classical field. We will then quantize it and get a quantum Klein-Gordon field. Okay? Right. I think I've told you what everything is. This is a real parameter. Okay. This is a real parameter. Okay. And there are some specific values of it that are nice, namely chi equals 0, which is called minimal coupling. And there's another nice one, which is chi equals n minus 2 divided by 4n minus 4, which is conformal coupling. And it's called a conformal coupling because if you have 0 mass and psi takes this value, then you can use conformal methods to solve that equation. I mean, you have a conformal equation, okay? So, namely, you can rescale the metric with a factor omega squared that is positive, and you can rescale the field with omega weighted by something and simplify the problem, or get a mapping between the two problems. Okay. And just a word of caution before we go to quantum field theory. The stress energy tensor of this guy up to signs, which I may have gotten wrong, is the following. So in particular, notice that the value of chi appears in the stress energy tensor, as you would expect. But notice that if you would have a theory where G is background structure, so for example Minkowski space, so that R is equal to 0, and you would imagine that that term would not appear. There's a curvature coupling, but there is no curvature. The curvature is 0. Well, it will still appear here in the stress energy tensor, okay, when you do the variation. It's because you're varying with respect to the metric, so even though the metric is a background structure, you're still using it as a gadget to get the stress energy. You're imagining it's background, but then you're paranoid and you vary it. Okay. So, well, keep in mind that even if you're minimally coupled, if you're non-minimally coupled, and even if R is 0, this term might be relevant for the stress energy tensor. Okay, just a little word of caution.
Even if R, the scalar curvature, but not the Riemann curvature? What do you mean? Even if R is 0, that term
will still be 0. So if you're in an Einstein manifold, then Ricci is 0, therefore R is 0, but this will still appear. But you can be even more dramatic. You can be in Minkowski. Riemann is 0 in Minkowski, and it will still appear, okay? Right. That's the
same action. Like if R is 0, you can put the C however you want it, as big or as small as you want. So it will have.
Yeah. Well, there's two things, right? I mean, there's the equation of motion, which where C will be irrelevant, right?
Yeah. Okay. But.
And there's the stress energy tensor, where you do this paranoid thing of varying with respect to the metric.
But if you fix the metric since you're in the action, like that doesn't appear if you're already working in Minkowski.
This doesn't appear in the equations of motion. Sure.
But in the action.
Well, in the action it appears.
I guess the question is, why are you taking variations with respect to the metric if the metric is fixed?
Yeah, because that's what people do, right?
That's the question, right?
That's how you define the stress energy tensor. As I said, I mean, it's very paranoid, right? You see, I mean, there's a reason why it kicks in, because you're imagining its background structure, but then you're using it to get another gadget, and it's non-dynamical, but you're varying with it. It's all very iffy, right? But I agree with you, it's very weird. But just keep it into account, okay? Okay. So there's the equation of motion, of course, which is the following. Up to factors. No, I think the factors are correct. Okay, that's the equation of motion, and this is the Klein-Gordon equation. Okay. So now, this is a classical field, and what I want to do is quantize it in Minkowski space. So the Klein-Gordon equation looks like this. So this is in Minkowski spacetime. So the idea of quantization now is to promote this to an operator. And the question is, an operator where? And the answer is an operator in some Hilbert space, in some functional space. It must act on some functions, okay? And the question is, what functions? And the answer is, we need to do a lot of work to see that. So quantizing this is tantamount to two things, right? So it means writing an operator, but it also means writing a Hilbert space where the operator acts, right? And the Hilbert space will have so-called positive frequency modes and particles and so on and so forth. We will build a Fock space, if you guys remember what that is. Okay? Right. So let me do something that will look completely mad, and then I'll explain how to make sense of it. I'm going to define this operator. And I'm going to write the Klein-Gordon equation like this. Okay, so that's the definition. Right? And then I'm going to write the solutions. Is anybody familiar with that way of solving this problem? Okay. It goes back to saying why it's very important to construct a space of functions. K is an operator. It must act on a space of functions, right? And we have to say how K acts. So here, K acts on F and G. You can understand cos and sine as some power series, right, as a Taylor series. But there's something else. If we had an eigenbasis for the operator K, then we would know exactly what it does, because it would just act as the eigenvalue, right? And this would just be cosine of some eigenvalue f, sine of some eigenvalue g. By the way, I forgot to say that I want to solve the problem subject to, of course, some initial conditions. Okay. So initial conditions are happily satisfied. Right? And now if I can solve the equation, if I can find the eigenmodes of K and realize those eigenmodes as spanning a Hilbert space, then I'm done. I have to realize K in such a way that K is self-adjoint to be able to give it a spectral representation, right? And self-adjoint operators are sort of the most important operators in quantum mechanics and in PDEs and so on. And solving a PDE problem, there's often the same amount of work in finding the solutions and in finding the space of solutions where those solutions live, such that the operator is self-adjoint. But the nice thing now is that, okay, let me solve then the following eigenvalue equation, right? And if I solve this eigenvalue equation, then I'm more or less done. Okay? So I want F and G. So FG complex support, data of complex support. Okay, so this notation means compact support and smooth. C infinity is smooth and C infinity naught is compact support. So what it means is that if you take R3 here, then the functions f and g are non-zero. The support of, okay, I'll tell you what the support of the functions is. The support of the functions is where the functions are non-vanishing, right? And then you take the closure of that, and that, so it's the closure of the points where the function is non-vanishing. So for example, if f is like this, and it does that, and then it goes that, then this is the support of f. And this is f of, well, whatever. This is f, and this is the domain of f. Okay, and this is support of f. Okay, that's the idea. Okay, and so this is a nice space of functions because I give you some initial data that is well localized, and then I use the Klein-Gordon equation to see how the field propagates starting out from that data. Right? It's very nice. Okay, and this satisfies that that equation, right? Provided that k does what we want it to do. Well, it satisfies it just by taking two derivatives. But then we want to see what k does, in what space it acts, and so on. Okay. So notice that at least the way in which we have written this, k must act, so C naught infinity R3 must be in the domain of k. It better be, okay? So let's solve this problem. Well, a very easy solution is plane waves, right? So k, so let's write psi equals e to the I k x. Psi equals e to the I k x. It's a plane wave, and k acting on psi is equal to k squared plus m squared psi equals lambda psi. Okay, so this tells us that the eigenvalues of that equation are k squared plus m squared. Now I'm interested in k being positive and self-adjoint. So you can see, you can see the values of lambda here that solve this equation are all real. And if I restrict to lambda positive, then it means k is positive and it's self-adjoint. Okay? So I'm going to write this as omega squared greater than 0. Okay? And then I can write the solutions that have. So the spectrum is real, it's symmetric. Where is it symmetric? Where? Well, let's take L2. Let's take L2 as a space. So what does that mean? It's the space of functions. Functions which go from R3 to R in our case, such that the integral v3x f of x is less than infinity. Okay, that's L2. Square integrable functions in R3. And k is a symmetric operator there, because you can integrate by parts twice the Laplacian on one of these vectors in L2. So let me do that explicitly. F kf d3x f plus m squared f. I integrate by part twice. I assume that, well, these functions better decay sufficiently fast at infinity, otherwise they wouldn't be square integrable. So I have no boundary contributions from integration by parts. M squared f equals d3x kf. Okay? So it's symmetric, and it has a spectrum that is real. So K is self-adjoint. So it has a spectral representation, and in particular the way in which I have written this here, I can replace all the K's by lambdas, right, in practice. I don't want to really spend time doing maths here, because that's not the point of this. But let's do that. T dot cos t, whoops, square root of lambda f plus sine t square root of lambda g square root of lambda. Okay. Provided we can write f and g in terms of these modes, right? And that we can do because we know that f of x is equal to the Fourier transform. Let me see what my convention is for that. Is equal to the Fourier transform e to the I inverse Fourier transform of f hat. So we can write f as a sum over these modes, as a sum over plane waves, which are in turn the eigenstates of this operator. So the eigenstates of this operator, and we write f as a sum over the eigenstates. So we write f inside this space, okay, inside L2. And this justifies what we have done here. And we write the solution. 3. And we write the solution in the following way. I'm going to write square root of lambdas omega and we know that, okay, I'll write it here, omega squared is equal to k squared plus m squared e to the I k x f hat k plus sine omega t divided by omega e to the I k x g k. Okay.
Benito, isn't it an issue that plane waves are not square integrable?
Of course, it's a technical issue. The point being is doing Minkowski space is hard Usually people quantize things in a box where you have discrete spectrum and everything is nice. It's not an issue, but it's a technical point. And the point being is that plane waves are distributionally L2. And this is expected because the spectrum of K is continuous. So the continuous spectrum contribution of an operator never has authentic eigenstates. It always has eigenstates with a pinch of salt. And this is the case here. So yeah, of course, these guys are not L2, but this is expected from standard spectral analysis. Right? This is standard theory. Okay, so that's a comment that we should write down, yeah? That plane waves are not L2, but that's fine because they are eigenstates of the continuous spectrum. So it's subtle, but it's a good remark. Okay. Okay. So now we have all the solutions. We have a space of solutions, which is basically all we need is that f and g have Fourier transforms. In particular, if they're C naught infinity, they do. But we could extend them to be just rapid decay. So for example, Schwarz functions in R3, right? They're rapid decay, they have Fourier transform of rapid decay. Functions of compact support that are smooth have Fourier transforms of rapid decay. So everything is reasonable here. And so we have the solutions to the problem. And now I would like to talk about the phase space of that classical space, because as you know, quantization is going from a classical phase space to a Hilbert space with operators on that Hilbert space. Okay. So the classical space of the classical phase space of solutions, you can look at it as pairs of F's and G's such that B, T, X in that form. So in that form. IE minus CT squared plus initial data. Or let's just be explicit. Okay, so it's a space of initial data, pairs of initial data. That's what the space of classical solutions is like. And because we said our solutions are in L2, in particular, Schwarz functions are in L2. Okay. Well, yeah. These are nice Schwarz functions, aren't they? So on. And we can write a symplectic structure here for two solutions, which I'm going to call phi and psi, and it's just going to be the standard canonical P, and this is R3 here. R3, and this is T3x. I think we went from Rn to R4, but that's fine. It's the same story. Did we? Yeah, okay. Okay. And so what are observables? So observables are functions on the phase space. They are functions on phase space. An observable O goes from phase space to R. That's a classical observable. Okay. So one nice way to think of them, since we have the symplectic structure, this is a symplectic space. So it's the only natural bilinear form that we have in the phase space. But if it's non-degenerate, and that's just a technical point, and it is in this case, then we can use it to get functionals on this space, right? Okay. So, for example, one observable, we're going to call it O phi, is equal to phi comma dot, right? So if I give you O phi acting on psi, this is phi psi, and this is a real number, right? So this is how I get observables on phase space. And the story is extremely akin to quantum theory, where, okay? So, and then the symplectic structure induces a Poisson bracket on the observables, which I can write like this. These are two observables, say O phi and O psi, and their symplectic structure and this is the Poisson, this is the symplectic structure, and this is the Poisson bracket. Okay, and quantization is going from Poisson brackets to commutators. For the Klein-Gordon field, commutators, of course. Okay, and let me just be a little bit more be very concrete so that you get this language and you're familiar with it. Let me choose an observable O phi equals this with phi coming from data with phi with initial data q phi equals 0, p phi equals, let me write it like this, q phi p phi equals 0 f1. And let me choose similarly O psi equals psi comma with psi with initial data q psi p psi equals f2 naught.
Benito, can you clarify your notation for me? What's q phi and p phi?
Sure. So p phi is phi dot at t equals 0. Q phi is phi at t equals 0. Initial data.
Okay.
Okay?
Then I have another question.
Yeah.
So is your relation for the Poisson bracket a definition or you derive it from somewhere?
That's a definition, yeah.
Okay.
You use the symplectic structure to give you the Poisson bracket. Yeah. Right. And what do I want to do now? Yeah. So omega phi dot is equal to the integral. So Q is 0 and P is F1 of dn minus 1 x n minus 1 P is F1. F1. So if I insert some chi here, I get the position of, I'll call them just Q and P. And similarly, where are you? Psi chi equals the integral dn minus 1 x n minus 1 f2 p. So chi has chi dot at t equals 0 equal p, and chi at t equals 0 equals q. All right?
I guess there's a sign missing.
Maybe. Maybe there.
Okay.
Yeah. And now I'm going to take, and now look, this is just a smeared position. Namely, it's a functional on position, and this is a functional over momentum. What does it mean? That what we have called O phi, which is this one, and this one we called OP, O psi. O phi takes Q, which is data here, let's say, with P trivial, and gives me integral of F1 Q. And O psi, well, takes QP, right? So takes chi, more precisely, in the way that we're doing it, and gives me the initial value and smeared. And this one takes chi and gives me it's smeared. It's a functional over the momentum. Okay. And then if I look at the Poisson bracket of O phi and O psi, then I just get, where are you? The integral of F1 and F2 t n minus 1 r n minus 1. The L2 product between F1 and F2. Okay. Yes. So that's a story. That's all classical. But the story is that these kind of, so think of it. Of course, there's a long we've gone a long way to get into intuition about this phase space and space of observables. But just think of the space of observables as mirrored position and momenta. This is the easiest way to think of it. So you take some P or some Q, which is in the phase space of the theory, and you give me a real number by integration, and that's an observable. Okay, it's a map. Okay, and I have half an hour, so that's good. And what quantization means is to go from this sort of relation to a quantum version. So let me just remind that. Remind you of what that was. F1Q F2P equals F1 F2, where it's understood what the integration and the measure, where we're integrating and what the measure is. I'm just writing it like that. Okay. So that's the Poisson. And what we want is, we want this. We want this. Something, maybe even this, perhaps with some factor, times the identity. And we want this to be acting on a Hilbert space. Okay, this is canonical commutation relations, CCR, canonical commutation relations. This is what we have, this is what we want. This is quantization, okay? Okay. So remember the solutions that we had, which I have just erased, that they looked like integral blah 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 cosine something omega t something plus sine omega t times something. This is what we had. So there's a very nice notion in field theory, which is useful when you have symmetry, which is positive and negative frequency modes. And if you write cosine and sine in terms of exponentials, you know, cosine e to the I omega t, blah, 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 plus e to the minus I omega t over 2, then we can write the field in the following way. And this you will find very familiar. Okay, with P plus K square root of so notice that these guys, phi plus and phi minus, I can get completely from initial data. Okay? Omega fk bar plus 1 over I okay CC. So phi plus star. Okay. This I can get completely from initial data. I've just rewritten the solution. In technical terms, I've done a little bit more than just rewriting the solution, but that's not important. I've sort of introduced a complex structure in some hidden way. Okay? These are in a sense complexified solutions. Okay? And now let us do something else that is nice. Let us call this a mode. And similarly, there's also a UK bar, of course, right? So these are mode solutions to the Klein-Gordon equation. These are mode solutions to the Klein-Gordon equation, and the initial data comes in these coefficients. These are mode solutions. These are mode solutions. These are mode solutions. And here is the initial data. Okay? Now, I forgot something, which is 2 pi n minus 1 omega 1/2. And now remember we have this symplectic structure here. Let me introduce an inner product. Chi and psi. This is an inner product. And I'm going to call it I'm going to call it I times the symplectic structure chi, comma, psi bar. And again, I have introduced this hidden barring structure here without going into much detail. But you can verify that this is an inner product. And this has a technical name that, is irrelevant, but this is called a Keller space. It has a symplectic structure and an inner product. Okay, just trivia if you want to Google it. Okay? And now look at this nice inner product that we have constructed. It has a very nice property. If I formally, so remember that as Yuri said, these modes are technically not in L2, and this guy relies on an L2 product here, hence this is relying on an L2 product of some sorts. But we still can get the following formal relation. Okay, this is a very nice property of these modes, and this is called Dirac orthonormality. And I have introduced, I didn't say something that is important. So I've done this decomposition into 2 bits, and now I want to introduce something called positive and negative frequency. So these modes we call positive frequency modes, and the complex conjugate we call negative frequency modes. And more precisely, the definition is the following. If you act with some Lie derivative of a time function, and in this case it's just a partial derivative, and you get minus I omega. So minus I omega is an eigenvalue of that operator, then you call this positive frequency mode.
Omega is always positive, no?
Omega is always positive. And if you get the opposite, then this is negative frequency mode. It's a confusing way of calling it, but that's what people call it in the literature. And it also, you know, you can also think of it in terms of the coefficient that stands here. One is the coefficient and the other one is the complex conjugate. So in the negative frequency mode, you have the complex conjugate. Okay? And this in a product, I want to introduce it in a space where I'm only considering the positive frequency part. Okay? So just to remind ourselves, I'm going to put a plus there. So this means that I only take positive it's a space spanned by positive frequency modes, right? And solutions of positive frequency, namely, they do not contain this, right? So an equivalent way of saying it is that the subspace spanned by this, you remove, right? In other words, you only want solutions where G hat is proportional to F hat in such a way that this is 0. That's the only solutions that's a subset of all the solutions that you can get. Now you're getting this constraint relation between initial data, and you throw away all the initial data that has that form, and you are left with a subspace, which is the subspace of positive frequency modes. Okay? And our aim is to use this positive frequency mode space to build the Hilbert space. And we are already on our way to doing that because we've introduced an inner product, which is what you need for a Hilbert space.
What's the issue if you keep the negative frequency modes?
Well, that's not an inner product.
So the issue is
Yeah.
you don't have a definition.
Yeah. The issue is the construction of the Hilbert space. Yeah.
And for the theory, what does this imply?
It means that particles have positive frequency, that the quantum particles that we will construct have positive frequency. They propagate to the future. Okay? Okay. So now, technical points aside, we have everything to quantize. Right? We have an inner product, we have some solutions, and so we've started out from a classical space of solutions. We have restricted to positive frequency modes because we want particles that propagate with positive energy to the future, and we've built an inner product there. So now we have a space which we can use to construct a Hilbert space. And there's a technical point that this space has to be completed to be a true Hilbert space. Blah, blah, blah. It's not important for now. I mean, it's important, but let's not go there. Okay. So we have our classical modes. UK. What did I call them? 5 plus K plus CC, right? That's a complexified. Actually, I only want the positive frequency part. And now I'm going to quantize. So quantizing is, as you all remember, going from these guys to operators, right? So I'm going to write this, the quantum field, as dn minus 1k uk a k, annihilation operator, plus, and now I consider to kill stuff in the Hilbert space, the complex conjugate of that, which is uk bar with the adjoint of the annihilation operator, which is a creation operator. And now this is a quantum field. And it acts on a Hilbert space. What is the Hilbert space? The Hilbert space is the space of solutions of the Klein-Gordon equation, which are of positive frequency, B such that B equals 0, such that phi minus k equals 0. So I'm imposing this relation. Well, integral blah 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 equals 0. That's fine. Let's just schematically write it like that. Vector such that this, right? And with the following inner product, such that the inner product between two guys is equal to W plus. Okay, that's the Hilbert space. And now operators act here. Okay. And now let us impose the canonical commutation relations. So let me introduce some notation. If I say A of V means the integral of dn, actually I want to introduce F here, dn minus 1 k, I think I wasn't using that, u k f hat a k. And then I want to call A star G equals dn minus 1 k uk bar G hat a k star. Okay? I want to introduce this notation, right? And with this notation, I can impose the following canonical commutation relations. So let me call this the solution coming from that f hat, which is built out of, as you remember, this is, let me change the notation because you might get confused, right? Let me call that phi plus, phi minus, and this is some sort of phi plus, and this is some sort of phi minus. Okay? So there's a solution here that comes from the phi plus bit, namely this bit, and yeah, let me keep here V and W. V, W, bar, W like that. Yeah, I want to call that the commutator, right? And if I don't have much time, but
this thing you get, right? Because a commutator is already defined. It's not that you are defining.
The commutator is defined on the algebra of operators, but but I'm telling what the commutator is.
Okay.
And we will see that everything will be consistent at the end. Okay? And it's a nice check to see that if you take V, VW with V, so V is what goes in here, so V has that form, right? It's a good exercise. I'm just gonna drop this because I've assumed that I've completed the Hilbert space and other technical points. So I'm gonna call it the inner product in H now. And it's a nice exercise if you follow the formulae and so on to get that this is simply the integral over dn minus 1 k v w. And from here you can still continue. So notice what's going on is we are using the Fourier transform and so on, and getting deltas out of these guys. Right? That's the idea. And if I assume that v and w are the Fourier transform of something, then I get the following nice relation: minus 1 x of the inverse Fourier transforms. Okay. And this is just an L2 product on this V and W. So again, how does this connect with the whole initial data story that I was talking about? Well, initial data helps me cook this phi plus, with which I label my operators, namely they create and they annihilate solutions in the Hilbert space. And a nice property is that you get that the inner product between those two solutions is just either an L2 product in momentum space or in position space, where these guys can be cooked out of initial data, okay, in the positive frequency region of the classical solutions. Well, of course, there's some other relations. Right. So with this, we can write the commutator in the following way. Okay, which looks suggestive. And finally, I want to call there's the following other relations. And finally, I can construct the following operators. And this equals I phi plus pi square root of 2. And I can get the usual and I can get the commutation relations in the usual sense, namely with phi and pi equals integral d n minus 1k. I'm calling them u, v, u, v, which is much like the stuff that we wanted to get, or if I want, I can use their inverse Fourier transforms to get exactly this form, which is the form of the Poisson, the Poisson algebra, right? And this is, of course, the, you know, this is, of course, the smeared version of the usual Poisson bracket equals commutator equals delta. So if I remove the integrals in an appropriate sense, I get a delta, right? However, that delta and that other way of writing things doesn't make much sense. So this is a more correct way of writing them, because now they're really quantum observables. They're taking some vectors in the positive frequency complexified space of solutions, and they're giving me a number in the sense that the Poisson algebra does the same in the phase space of the classical theory, right? So finally, what is the... And by the way, I'm just switching between momentum and space. I can represent this as momentum vectors with this L2 product, or I can represent them as space guys with this L2 product, the solutions. It's just a matter of whether I choose to take the Fourier transform or not, right? It's all very neat, I would say. So finally, so we've talked about the Hilbert space of the theory, but we haven't, so this is a one-particle Hilbert space, but we haven't yet constructed a Fock space where these operators really can act more naturally because they cannot act successively and stay in the Fock space. And the Fock space is what? You take the Hilbert space that we constructed. First, let me tell you what the vacuum is. You declare the vacuum of the Hilbert space to be whatever is annihilated by the annihilation operator. Okay? And when you act with the creation operator on the vacuum, then you get a vector. You get a vector in the Hilbert space, right? You might call it, you might decorate it if you feel pleased about that and call it like a ket, if you will. Okay, and finally the Fock space is just acting with creation operators successively in the vacuum, and you get a Fock space which is equal to sum from n equals 0 to infinity of these symmetrized tensor products, because you're in a boson space, right? With h to the 0, let's say 0 equals c, h to the 0 equals c, and this looks like c plus h plus symmetrized h plus ta. Okay, that's the Fock space of the theory. And vectors and these operators act naturally on the Fock space. I can just create more and more complicated Fock space vectors by acting with the creation operator. So a typical element of the Fock space will look like, say, this, right? 32, which is a number, complex number. Why not? It's a solution to the Klein-Gordon equation, the number 32. This is like that. Plus some vector, plus symmetrized, plus I can get some V1, V2, and so on and so forth. Actually, let's just keep it serious. Okay. So this is what a vector in let's say V3, V4, V5 with some coefficient alpha with some coefficient beta there. Okay, that's what a typical vector looks like. And all these V's are exactly what we have constructed here. So these positive frequency solutions, complexified solutions to the Klein-Gordon equation. Okay. And finally, I need to tell you how the creation operators and so on act on this guy. And here I'm going to be off by a factor. There's a factor that I always miss, but if I act with a creation operator on V, then I just get, let's say, with taking vector W, then I just get sim W plus alpha W V1 V2 sim plus beta blah blah blah, you get the idea. And there's a factor here that I'm missing, is 1 over square root of, it's a constant factor, so modulo constants, mod constants. And then the annihilation operator simply takes the contraction V using the inner product plus, let's just write it like this, it's easier, right? We don't need to, so we write it like a vector, like that, comma, the contraction with V1 symmetrized V2. Again, factors missing, etc. So in other words, when I act with a creation operator, I'm moving one step up in the Fock space. I'm going from n particle states to n plus 1 particle states. When you act with an annihilation operator, I go from n particle states to n minus 1 particle states.
So this is confusing once you took out the 32, right? Because
yeah,
in this notation you should add a zero.
Yeah, you have to
Sure.
Particle entrance.
the number.
well,
Because A acting on B, the first entrance is a real,
it's a real number.
complex number.
Sure, it's a complex. Sure, yeah. Well, there's an entrance which is a number here.
Zero, let's say.
Yeah, or 1 or whatever. Okay.
Okay.
Anyway, that's the end of the story. We have our operators and we have our Fock space and we've quantized things. We can then use this formalism to get the endpoint functions by calculating brackets in the usual way. Yeah, and I think this is more or less it. And let me say that for those of you who haven't done quantum field theory, this might have been a little bit fast, but then we'll take it slower, I must say. And for those of you who have done quantum field theory, I just wanted to give you an overview with a little bit more precision than the usual first 3 pages of a quantum field theory book, right? Okay, so that's it.
May I ask or comment on something?
Sure.
So you define the positive and negative frequency modes with respect to a given direction in time,
Yes.
right? But in Minkowski we have an infinitely many directions of times that you can get out of
Yeah.
the one you use through Lorentz transformations,
Yeah.
right? So you want to comment on this?
Yeah, I mean, of course you can act with Lorentz transformations represented unitarily, and the form of the modes, as you can see, is you can, I mean, it's
I mean, the important point is that what you call positive and negative modes won't
Yeah.
change.
yeah, that's
Right.
right. That's right.
So every observer or every notion of time
Yeah,
would coincide
that's right.
here.
But I could have chosen, you know, that's a very good point what Yuri's saying, because of course now we've done flat space-time quantum field theory and everything, you know what with time flows you have in some sense you have these time like killing vectors, you have this time symmetry, time translation symmetry, and you want to use it to tell you how your modes propagate. The point is that in curved spacetimes you don't have that.
I'm sorry, but I have a class now.
Yeah, so we're leaving. Yeah. So in curved spacetimes you don't have that, and so this formulation is ill-suited for that, and that's what we're gonna learn. Okay.